Okay, welcome to the week 7 review. Now, you may notice that even though we were doing simple harmonic motion in this week, that this is not a simple harmonic motion problem. And the reason why is because we did the one simple harmonic motion AP problem that has been on past exams already in class. But this problem does a really great job of practicing that qualitative, quantitative translation that is going to be the first question on the AP exam. So we have a long track that's inclined at an angle of theta to the horizontal, has small speed bumps on it. The bumps are evenly spaced a distance d apart as shown. The track is actually much longer than shown with over 100 bumps. A cart of mass m is released from rest at the top of the track. A student notices that after reaching the 40th bump, the cart's average speed no longer increases. Okay, so that's important. So the average speed no longer increases, meaning the cart might speed up or slow down, but the average speed stays the same. Okay, reaching a maximum value V average. This means the time interval taken to move from one bump to the next bump becomes constant. So, consider the cart's motion between bump 41 and 44. In the figure below, sketch the graph of the cart's velocity as a function of time from the moment it reaches bump 41 till the moment it reaches bump 44. Okay, well, I know that as this cart M is traveling down, we have a force Fg and a normal force Fn. And remember, a component of this Fg points down the incline. So even though the average velocity is the same, the car is still going to speed up in between the bumps. Okay? So I'm going to go ahead and show that. Now, the average speed is the same, which means the amount the car speeds up should be the same approximately for each interval. But the thing is that when you hit a bump, you slow down. It's no different than a speed bump. So we're going to slow down over the bumps. So our graph should look something like that. It's definitely super weird. Then it says, over the same time interval, draw a dashed horizontal line, V average, and label this V average. So how do we find the average velocity? Well, because all of these are the same, the average velocity is just going to kind of go right across the center of them. So my dashed line, that's not the center. That's not the center. My bad, guys. The dashed line, that's a little bit better, is going to go right like that. Now it says label V average, so I got to make sure I label it. Okay? And it's a horizontal line because, like it says, the average speed is not changing. So let's check my points for that. All right. So part A1 is 3 points. So I have a constant velocity upward slope for each segment. That is because we're accelerating. I have that. For having a velocity reset abruptly at each bump. I have that because we got to slow down. For having the same maximum value in each cycle. I have that. And then I need 1 point for drawing a V average line that's horizontal consistent. Yep, I have that. Hooray! I got 4 points of the 12. Okay, so now suppose the distance between the bumps is increased, but everything else stays the same. So there's more distance here. So let's say this is our distance D now instead of that. So it looks like we now have more room to accelerate. Okay, so is the maximum speed of the car now greater than, less than, or the same? So I'm going to say greater than, okay, with more distance between bumps, the car accelerates for a longer time, leading to a larger max velocity. Okay. So I have my claim that I have greater than. Okay. I have evidence and I have reasoning. Okay, so let's check my points for that. So it's a 2-point answer. So my correct answer is 2 points, but I don't get points for that. I get points for indicating that there's more time, which I said, and for connecting the cars more time or more distance to accelerate. And I said that. I even used the word accelerate. All right, let's do, Oh, and one thing they did say is they do have a solution for terms of energy. So for indicating that the potential energy difference increases due to increased height between successive bumps. So more change in potential energy leads to more change in kinetic energy, leads to more change in velocity. So if that confuses you, they're basically saying that this little triangle does not have a great change in height, whereas if we increase that distance traveled, we have a greater change in height here, which means we have a greater change in potential energy, which leads to a greater change in kinetic energy, which leads to a greater change in velocity. Okay, C. So the bumps are returned to their original spacing. The track is tilted to a greater angle. So instead of maybe being a shallow angle like that, or like that. Right? The maximum speed of the car, greater than, less than, or the same. So with a greater angle, theta. Okay, remember, let me draw this. Okay. The thing causing the acceleration in this problem, meaning the thing causing the car to travel down the incline, is this component of gravity parallel to the incline. So that FG parallel is FG sine theta. As theta increases, the sine component increases, which means FG increases. Okay? And if that FG parallel increases, then that leads to a greater acceleration, which leads to greater maximum speed. So briefly explain your reasoning. So the max speed will increase because the parallel component of gravity increases with increasing angle, leading to greater acceleration. Okay, and greater acceleration leads to more speed. So let's go ahead and check my points on that. So C, what's greater than? For indicating acceleration is greater. I got it. For indicating that the component of gravity is greater. So I got that. So there is another alternate solution in terms of energy. So it's pretty much the same as the one before, that the potential energy difference increases because we have an increasing height difference with the same distance if we're at a steeper angle, and that increase in potential energy is an increase in kinetic energy, which leads to more speed. So actually B and C in terms of energy have the same answer. Who knew? Okay, on to part D. Here's the fun part, the equation part, which all of you guys don't love, but it's okay. All right, so before deriving an equation for a quantity such as V average, it can be useful to come up with an equation that's intuitively expected to be true. That way, the derivation can be checked later to see if it makes sense. So a student comes up with the following equation for the cart's maximum average speed, where C is some positive constant. We don't know what C is, but it's a positive constant. So to test the equation, the student rolls a cart down a track with speed bumps many times in front of a motion detector. The student varies the mass m of the cart with each trial, and everything else the same. The graph shows the student's plot below. So we need to see if the data is consistent with the student's equation. Okay, so we have V versus m. So according to this equation, V average is directly proportional to mass. So that means that if I double the mass, then I should get double V average. It'd be great if I could spell correctly. So let's look at 1 to 2. So at 1, a mass of 1, my velocity is at about 1.5. At 2, though, my velocity is only at 2. So that's not a direct relationship, which means this data is not consistent. So we can say something like, according to the equation, V average and M have a direct relationship, but in the graph, doubling M does not double the average. Okay. So I'm talking about what a direct relationship means in reference to the graph. And the graph, even though it looks linear, actually is not, because we don't have a doubling of M leading to a doubling of V average. So let's check my points there for D1. All right. So correct answer, no. Okay, so I get 1 point for indicating that V average is not proportional to M. Good. And for connecting the equation to the data. So I said that. So I referenced the equation and I referenced the data. So example, the y-intercept of the graph is not 0, but the equation indicates that it should be. That is one way of going about it. Doubling the mass from the graph does not double V average, but the equation indicates it should. Okay. So basically what that y-intercept is saying is, if M is 0, according to this equation, V average should be 0. But if we look, V average, if we extrapolate the data, would not be 0 when mass is 0. So that's what that second part was talking about. All right. So another student suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. So does the equation make physical sense? All right. So basically, this question is asking you to refer back to B and C, okay, where we said that as theta increases, the average increases, and as distance increases, the average increases. Okay, so as theta increases, V average increases. Well, as this theta increases, sine's going to increase, which is going to lead to a V average. So that's good. Now we have to look at D. Well, according to the equation, V average and D, the distance between the cars, have an inverse relationship, which would mean that increasing D actually leads to a decrease in V average, which is not the case. So this would be a no. So according to the equation, V average and D have an inverse relationship, which is incorrect because, as stated in B, increasing the distance leads to an increase in V average. And let's check my points for that one. Okay. So for indicating that distance dependency is incorrect, that's what I said. For indicating that according to equation, your greater distance leads to a V average, or for stating or implying that contradiction between the inverse relationship and the reasoning in B. So that's what I said. Okay. So their example is, according to the equation, a larger distance corresponds to a smaller V average because they're inversely proportional, but according to the reasoning of part B, a bigger distance between bumps leads to a larger maximum average speed, showing that the equation is implausible. So I said that, but without such big words. Right? So that is the end for this solutions video. Thank you for tuning in. It is always much appreciated. Not that you, well, yeah. All right, so long.